So Petar Korponaic is an experienced software engineer and entrepreneur. He is a founder of Quantastica, a quantum computing startup based in Finland. And I guess the first person that created a quantum computer simulator in JavaScript. Correct me if I'm wrong, but as far as I remember, that's the case.
I'm not the first.
Sorry?
But this is how it started.
This is how it started, yeah. And his passion is software development, acceleration, and code generation. And this is something he will be talking about today. Okay, Petar, can you start screen sharing?
Okay. Okay, thank you, Michal, for introduction, and thank you for inviting me to this event. As Michal says, my name is Petar Korponaic. I'm founder of Quantastica. Quantastica is a startup from Finland, Helsinki, and we are focused on programming tools for quantum computing. We are a team of 5 people distributed in over the globe. So part of the team is in Serbia, other part is in India, and headquarters in Finland. And today I will talk about automated quantum algorithm design. So, by the way, just to say that my presentation will be much less scientific. My background is, I'm from computer science. I'm a software engineer, and this presentation is much more which less formulas and less mathematics, but I hope it's not too light for this audience. So let's start with what problems we have today. Maybe this is not I mean, this audience already know what are the problems, but for completeness of my presentation, let me say that we have two groups of problems. One is quantum hardware, and another group is quantum software. So quantum hardware is something that we much more often see in media, that we read about better and better quantum computers. And so in quantum hardware, there is problem like noise, qubit connectivity, number of qubits, and other problems. And quantum computers are improving every day. And but other, a little bit less popular problem is quantum software. So even if we today have a perfect quantum computer, we don't have algorithms. Actually, we have only few algorithms developed to date. And in order to solve some real world problem, it's very challenging to make a quantum algorithm. So problem with quantum software is that first of all, classical algorithms cannot be used on quantum computer, because quantum computer is a completely different machine than classical digital computer. Then designing quantum algorithm is challenging, because we are dealing with quantum mechanical properties like superposition, entanglement, interference, and so on. So building blocks of quantum algorithm are properties of universe which are by itself hard to understand, and we are trying to make to solve problem using those those building blocks. So it's very challenging. And quantum software is unexplored space, which is not surprising because quantum computing is very young field. So there is a lot of things to be discovered here. And maybe, who knows, because now we have quantum computers that cannot be simulated classically. For example, 64-qubit quantum or 63-qubit, what is latest IBM quantum computer, cannot be simulated classically, or maybe, I mean, you need extraordinary amount of memory and CPU power to simulate that computer, that quantum computer. So now maybe we already have a computer capable of running some. Maybe we already have quantum advantage, but we don't know because we don't have algorithm which we will run on that computer. So this is unexplored, and we decided to try to automate this process of designing quantum algorithms to employ robots, as I like to say, and because I believe that quantum algorithm design is a job for robots, not for humans, because it's really really hard, and in near future, when we reach perfect quantum computers, I don't think that humans will make algorithms. It's more likely that robots or artificial intelligence will make algorithms, and we are working on that. And we already have actually the tool, and we already have users of our tool. So it's not science fiction. It's maybe it sounds like science fiction, but it's not. So let me start from the very basics. So what is how quantum program looks like? We have this psi here is state of quantum computer. This is state vector, which this is how a quantum computer is initialized at the beginning of before running the program. All qubits set to 0. This is by protocol, and because we cannot directly write data into state of the quantum computer like we can do with classical computer. We need to make quantum program which will encode our input data into state. This is called state preparation. And when we have data encoded into state, we execute main program, which is data processing, which evolves state vector or mutates state vector and produces final state, which we measure, and we get output data out of it. So this is how this is how usually quantum program looks like. And possibly we have one more block here before measurement. Maybe we can have some data decoding or some preparation for measurement, changing the base or something. But anyway, this is how quantum program looks like. Now, as different picture, so let's zoom one block here. So we have state vector, which we and quantum program is unitary transform. It can be described with unitary matrix, which produces the final state. So this is initial state, this is unitary transformation, or quantum algorithm, quantum program, which produces final state. On quantum computer, we cannot run any unitary matrix, arbitrary unitary matrix. because quantum computer has a fixed instruction set. Usually this is only few unitary transformations or only few gates, usually 3, 4, or maximum 5 gates, which is common. And this unitary is actually so we need to decompose this unitary, this quantum algorithm. We need to decompose to instruction set of the quantum computer, which is supported by quantum computer. Now, if we want to solve some real world problem on quantum computer, we have data. We have let's say that we have some function. We have input data and output data. Now we can encode input data into initial state, and we know that we expect some output data in a final state of quantum computer. Now, question is which unitary transform or which unitary matrix or which algorithm to perform to produce final state from our input state or to process our data. Now, even bigger problem is that we actually need multiple unitary matrices which are from our instruction set. So this is our challenge to find this program. Now, trivial example is quantum adder. To add two numbers on quantum computer, of course, quantum computer it's much easier and cheaper to run to add two numbers on digital computer. But just for illustrative example, let's see how quantum adder. Let's talk about quantum adder. So we have operands and results. So, for example, 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1, and so on. 1 plus 2 is 3. So this is our input. This is input data. This is output data. And now if we want to to add numbers on quantum computer, we need to encode this input data into initial vector, and we expect these numbers in a final state of quantum computer in final vector. So question is which unitary transform to perform which satisfies this equation. So with which unitary to multiply all this this initial vector to get this output vector. So this is our question, or even better, decompose to instruction set which set of unitaries to perform on or which set of gates to perform on quantum computer to get results. So this is the problem, and what we do with quantum algorithm with tool we call quantum algorithm generator is that we do reverse engineering of quantum circuit. So we find quantum circuit from a set of vector pairs. So input state and output state is one pair of vectors, and input into generator is multiple pairs of state vectors and instruction set. It can be any instruction set. It's best if this is some universal instruction set, but can be any set of unitaries. And output from the tool is quantum circuit or multiple quantum circuits, which solves this this problem. Another example is quantum Fourier transform. So we have a signal in time domain on input state, and which we encode into input state, and we have the same signal in frequency domain, which we encode into output state, and these pairs of vectors is input plus instruction set, and output from the tool is well-known quantum Fourier transform. This is another trivial example. Now, how it works. So we have input data and output data. So we have input into function, and we know what to expect at the output, because in case we have algorithm which works on classical computers, so we can produce inputs and outputs. The similar how we train neural networks. You train neural network with inputs and expected outputs, and neural network learns the algorithm, but it never give you the program. It give you the model, but our tool learns the algorithm and gives you the quantum circuit. So we have input data and we have encoding rules. This is something which you can experiment, because you can encode data into multiple ways. There are many ways to encode data. For example, in that quantum adder circuit, you can encode it binary by setting qubits on in 0 and 1 state, which is binary encoding, or maybe you can encode it in Fourier basis, like with QFT. So at the input you can use QFT to encode it into different domain, perform calculation, and then decode back with, for example, inverse QFT. There is many ways to encode data. It depends on what is the problem, how data looks like, how many how big is data set, and so on. And using these encoding rules, we encode data we make small quantum circuit which actually does state preparation and produces. We run that on simulator and produces a vector, which is in our case initial vector, and we perform the same with output data. For output data, we also have encoding rules how that data is encoded into state vector, and we produce final vectors, and we have initial and final vector, which is input into generator. What is not shown on this diagram is also that input to generator is instruction set as well. And from initial and final vectors and instruction set, generator produces quantum circuits. How we do that? We use machine learning in 3 steps. First, we analyze vectors. We find all we can learn from vectors. So which qubits are entangled, which angles we can expect in gate parameters. Maybe we can predict that in some cases not, and so on. Then we produce candidate circuits, which is set of circuits that are possible solutions for the problem. And because instruction set often have parameterized gates, then we send all these candidate circuits to optimizer, which is trying to find correct angles for correct parameters for gates, and it discards wrong solutions and outputs correct circuits. So for the same problem, we often have multiple circuits at output. Sometimes we have thousands of circuits at output. Okay, so we can reach only, at the moment, we can reach up to 6 qubits, but it depends on multiple factors. So we have something which we call generator volume, similar to quantum volume. So we have finite how to say power of generator, and depending on number of qubits and depending on depth of the output circuit, and depending on instruction set, how many gates there are in instruction set, and how many angles, how many parameters we have in instruction set, we can reach less or more qubits or less or more circuit depth and so on. So this is generator volume. Then when we find the small scale circuit, so as I said, we can reach up to 6 qubits, or more typically we can reach 4 qubits, but for some problems we can reach 5, 6, and even more. So we produce only small circuits for small scale problems. And then we are able to scale up the circuit if we can find, for example, 3 qubit, 4 qubit, and 5 qubit circuit for the same problem scaled to multiple qubits. Then we use machine learning to automatically scale the circuit. For example, this is a 2 qubit version of a problem, so we have 2 qubit circuits. Then for bigger version of the problem, 3 qubits, we have 3 qubit circuits, and so on. And we feed that circuits into autoscaler, which produces theoretically unlimited number of qubits, qubit circuits. And my time is running out. I have only a few slides, so I will try to be very quick. The purpose of the generator is to find the quantum algorithm for the function based on input and output data. Find quantum algorithm for Boolean function from truth table. As a side effect, our tool can decompose unitary matrices. It returns shallower circuits than any known method, but is time consuming. So it can take minutes, sometimes hours to decompose unitary. Also, we can transpile circuits, and again, we return a shallower circuit than any known method, again, time consuming. This is video which I will not show here. We solved IBM quantum challenge in few minutes. Just a second to move to next slide. Okay. And where are we now? So 4 plus 4 up to 6 qubits on single computing node. Our tool is capable of running on high performance computer. We are using MPI protocol. It's written in C language. It's integrated with Quantum Programming Studio, so we have UI. We have HTTP API, which is implemented in the Quantum Programming Studio. We have Python API. It's in development, and next week, in Friday, it will be possible. It will be available. Core algorithm is under active development, so we are trying to reach more generator volume, more qubits, or more or deeper circuits. And we have first users, companies in private beta, and that's it. That's it. That's it from me. I hope I didn't went out from time frame. And I'm happy to answer your questions.
Great. Thank you a lot, Petar. So, do we have any questions from the audience?
Yes, I have one.
Yeah.
What paradigm of machine learning are you using for your generator?
What paradigm? So we are using multiple, because this is pretty complex process. We use many different techniques for this. For example, depending on which stage we talk about. So so we use, for example, optimizer very frequently in multiple stages. Then we are using sequence generator or sequence LSTM networks. I'm actually not sure, because my colleagues who are working on programming knows better. But I hope this answer is satisfying.
Yeah, to some point. Yeah, thank you.
Another question?
Sure, I'll ask a question. I'm curious if during the early development of this product, if you noticed any of the optimizations devolving to lookup tables, or essentially, since you're learning the Boolean functions, did you notice any? How do you prevent against some of that?
When talking about Boolean functions, what we do, we actually only produce vectors from truth tables, and actually all we do is from vectors. So we didn't research a lot in that direction. We only take truth table, produce input and output vectors from it, and send that to generator. I hope that I understood the question well, so please let me know if.
Yeah, I was meaning that if that's all if you're just passing the input and output vectors, like, I guess what I'm wondering is, for some of the simpler functions, if you notice that you've essentially trained something to become a lookup table, essentially, a QRAM.
No, we don't do that. But good idea.
No, I was saying that wouldn't actually be a good idea, like in the sense that I guess your algorithm is already working correctly in this way, but I would think that you wouldn't want just like with machine learning, if you don't vary the input, you can end up just training completely on you can have 100% accuracy, but because you've essentially learned all of the input. It's all right. I was curious if you had encountered that during the development of the program.
Yes, actually, it works with any pair of vectors, so it doesn't depend on which. So on our training set, we are training it on different levels. So we are not trying to train and to learn some circuits and to solve one class of circuits and other class not to solve. So whatever is your vector, your pair of your vectors or multiple pairs of vectors, it will give you a solution. If circuit is not if you don't have too many qubits and if you don't have too deep circuit at the output. So this is, let's say, additional information on your question. And by the way, we have limited resources because we are early stage startup, and this is pretty consuming on resources. So we have only 4 companies actually using our tool at the moment in private beta. It's early access, but you can, if somebody is interested, you can register on our website on quantastica.com. There is a register form where you can request access to generator. Access is free at the moment, but we are adding, we are manually picking who we will get access. So you can try, you can register, and it's possible that we will allow access to whoever is interested to try the tool.
Okay, Petar, once again, thank you very much. I will like to finish the official part. So thank you both, Ryan and Petar, for the talks, and I hope we'll see you again in the next QRST in the next month. And now I would like to finish recording. Alba, actually, you are the host, so you need to click the button.